Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In this lesson, we're going to look at making a solution from a solid, and we're going to look at making a solution from a more concentrated solution. The math we're doing is pretty much exactly what we've been doing so far. So the only real new stuff we're really dealing with is the actual preparation of a solution. So the first type of solution we're going to look at making is called a primary standard solution. Now, a primary standard solution is made from a solid. So this would be the dissolving of a solid into an exact volume, and then that would be used for whatever you need it to. Now, the volumetric flask is the piece of apparatus that is very important to making a standard solution. So they come in sizes small from 25 all the way up to 25 milliliters all the way up to about 10 liters. So you can get huge ones. They're very accurate in measurement, and it's more accurate the smaller it is. So I'll talk about the volumetric flask a little bit more once we get to the actual process of making the solution. But what we're going to start with is something familiar, which is just calculating a mass using our C is equal to M over MV equation. So here's the question. It says, how many grams of potassium chloride are required to prepare a 250 milliliter solution that has a concentration of 0.50 moles per liter? All right, so the question is, what is the mass? They've told us what the substance is. It's potassium chloride, which is KCl. So looking up their masses and adding them together, so 1K and 1Cl, I have a mass of 74.55 grams per mole. I have a volume, but I have to make sure to convert this into liters. So there's 1,000 milliliters in a liter, so this would be 0.250 liters, and the concentration that they want us to make is 0.50 moles per liter. All right, so to clarify again, what we need to do is we need to figure out the mass of the solid we need to dissolve in order to make a solution of a very specific concentration. In this case, it is 0.5. Now, our volumes that we use, and in this one it's 250 milliliters, are really dependent on what size of volumetric flasks we have ready for us to use. So most schools would have like 100 milliliter volumetric flasks for students to use. In this question, it's a little bit larger, it's 250. So we can use this equation, C is equal to M over MV, in order to figure out the mass. But of course, we need to rearrange this in order to get it to isolate mass. In order to do that, I'd multiply both sides by MV. That would cancel those out. And so to get the mass required to be dissolved, I would go mass is equal to CMV. Now all I need to do is plug those values into the equation. So the concentration is 0.50 moles per liter. The molar mass is 74.55 grams per mole. And the volume is 0.250 liters. So if you look at the units, they're going to cancel out nicely. I got moles canceling with moles, liters canceling with liters. So I'm left with a unit of grams. What I'd like you to do right now is just pause the video, put that into your calculator, and see if you get the right answer. Okay, so I got an answer of 9.31875 grams. Now, most scales will be measured to a hundredth, so that would get us to this point here. I'm going to round that 8 up. So if you were in an actual lab, you'd measure out 9.32 grams. If you're in a fancy lab that has a scale that goes to 1,000th, then you'd be able to try to measure out 9.319 grams. But we don't have one that is that accurate. Okay, the next part, and this is the new part, is like, how do you actually make this if you were in a lab? Like, how would I go about doing this? And so what I would start with is I would start with a small beaker, at least half the size of the volumetric flask. So our volumetric flask is 250 milliliters. So I'd probably grab a beaker that would be about a 100 milliliter beaker, which is less than half the size of the volumetric flask. Then what I would do is I would put it onto a scale, and I would zero the scale so that the beaker essentially weighs nothing to the scale. And then I would dump in my measured mass of 9.32 grams of KCl. So I'd measure it out using a scupula, I'd put it in there, I'd keep adding it until it reached 9.32 grams. And then I'd go back to my workstation and I would have my beaker, and in the bottom of my beaker I would have 9.32 grams of the solid down here. Good. Now what I would do in my third step is I would add deionized H2O to roughly, I don't know, 80 to 100 milliliters in there. And then I would stir. So I'd add the water, and then the fourth thing I would do is that I would stir it until there was absolutely no solid left. It has to be completely, utterly, totally dissolved. Now once I have that, my fifth step here, so now I have a beaker and it looks clear and colorless. I've dissolved the potassium chloride, which doesn't have a solution color. So now I've got aqueous KCl. And I need to transfer this into a volumetric flask. So the volumetric flask has a really skinny neck, and then it has kind of a bulb on the bottom of it. Okay, and it has a line on it. And on this line, this is what we would measure up to. So up to that point, we would stop adding water to it. So the first step is I would put my funnel in it. Okay, so I'd have a funnel, and I'd take my solution and I would pour it down, and it would fill up to, I don't know, roughly about there. If this was, 80 to 100 milliliters in here, and this is a 250 milliliter volumetric flask, so this is 250. So I'd dump that solution in. I would also rinse. I would rinse the beaker of all of its contents in, and that would bring up the level a little bit more. Then in my next step, in my sixth step, I would have to add H2O up to this line, which is called the meniscus. So I'd have it go up to there. Now if I zoomed in on the meniscus, so if this was the meniscus, if this was the neck of the volumetric flask, there'd be a line like this. My solution would get filled up to like this. The water would bend down and touch the top of that line. That's the measurement line. And this would now all be filled with my solution. So I've done that. I would have rinsed the funnel and taken it out. And then in my very last step, my seventh step, I would put a cap on the volumetric flask. So it would be capped off. And then I would invert 10 times. So I'd turn it upside down and then back to right side up. I would do that 10 times to ensure that it has been mixed properly. Once that's been done, I've made a proper solution from a solid, which is called a primary standard solution. Okay, so now this is your turn to try to do a very similar question. It's just a different volume, a different concentration, and we're using a different substance. So what I'd like you to do now is try to answer 2A and 2B on your own, and then check your answer when you're done. So I'd like you to pause the video now, try to answer 2A and answer 2B, and then unpause it and check your work after you're done. Okay. Now that you've had a chance to do the question, let's go through how we would answer it. How many grams of potassium permanganate? Okay, so first thing I do is I look up potassium and permanganate. So permanganate is MnO4 minus. So together that is KMnO4. I need this in order to get a molar mass. And it says are required to make 100 milliliters of solution. I have to do a conversion there. This is 0.1 liters. That has a concentration of 0.5 moles per liter. So let's write down everything we are missing and what we need. Okay, so our mass first is what we're looking for. Plugging in the mass of 1 potassium, 1 manganese, and 4 oxygens, I got a molar mass of 158.04 grams per mole. And the concentration is 0.50 moles per liter. And again, I have to be doubly careful that my volume here is in liters, 0.1 liters. So again, C is equal to M over MV. When you rearrange this, it's M is equal to CMV. And then you can plug in your numbers. So we got 0.50 moles per liter multiplied by the molar mass of 158.04 grams per mole. And then lastly, the volume of 0.1 liters. And if we look at the units, the moles cancels with the moles, the liters cancels with the liters, and I'm left with an answer in grams. So let's put this in. So I got a mass of 7.902 grams. And so most scales would go to 100th. So the mass I'd measure out is 7.90 grams. Okay, so how would I do this? With my beaker, I have to go at least half the size of 100 mils. So I'm going to grab a 50 milliliter beaker. So this is going to be 50 milliliter beaker. Put that on a scale. And I'm going to zero that. Okay. Then I'm going to add into this 7.90 grams of KMnO4 solid. And then I'm going to go back to my station. And right now I would have my beaker. And at the bottom of it, I'd have KMnO4. Probably should have used purple since it's purple. That's okay. So I got 7.90 grams of permanganate in there in my 50 milliliter beaker. And I'm going to add in H2O. And then I'm going to stir it until absolutely all of the solid is dissolved. There's no solid left in that beaker. So now what I would have is a solution, approximately 50 milliliters, maybe 40, 45. It doesn't have to be exact, of aqueous KMnO4. So I've got a 100 milliliter volumetric flask with a line on it there. And what I'm going to do is I'm going to take and I'm going to pour this solution through a funnel. So I'm going to take and I'm going to pour that in, and it's going to fill part of it up, about part of the way. And then I'm going to rinse. I'm going to rinse out the beaker, make sure that that's really good. And then I'm going to top up the solution with deionized water up to that line where the water bends above the meniscus and comes down. And then I'm going to cap off the top of the volumetric flask. So I'll put a cap up there so it's closed, and then I'm going to invert 10 times, and then I've got my solution. The second way of making a solution is by diluting a more concentrated solution. So you could have a primary standard solution of high concentration and then dilute it down so it's weaker. Or you could buy a concentrated solution of something like an acid. So for instance, we don't have solid hydrogen chloride that we can dissolve and make our own solution. So we would buy a very concentrated solution from the chemical company, and then we would dilute it down for the use in the classroom. So very common with acids. Now, if you are diluting something, and again, if you don't understand what diluting means, it means just to make it less concentrated. So if I dilute my kids' orange juice all the time because orange juice comes so concentrated and so sugary. I'll pour a glass, a half or a third full of orange juice, and then I add water to it and I dilute it down. Diluting just means you're adding water to something. Now, if this is true, then the moles of whatever we're starting with at the beginning, I'm going to call it initial, is equal to the number of moles of the solution in the end. It's just the concentration of it that has changed. So for instance, using my orange juice example, when I pour the orange juice into the glass and then I add water to it, I haven't removed any orange juice. I've just added water to it. So if I'm preparing a solution of sulfuric acid and I pour a small amount of sulfuric acid into a volumetric flask and then I add water to it, the moles at the start is going to be equal to the moles at the end. The only difference is the concentration is changing. Now, if you're wondering, why is he talking about moles here? We're always talking about concentration. The reason why is this. When we have C is equal to N over V, and we rearrange it for N is equal to C times V. So if my moles at the start are equal to the moles at my end, then the concentration I normally have times the volume I normally have has got to be equal to the new concentration and the new volume. So we call it C1V1 is equal to C2V2, where C is concentration, V is volume, and then the 1s and 2s just stand for, the pre-diluted or the concentrated solution, and it doesn't matter which one you put first. I don't have to put the concentrated solution first and the diluted solution second. It's just saying these are the combinations of. Okay, so let's look at a question. This is, how would you prepare 500 milliliters of 1 molar, remember molar is moles per liter, H2SO4 solution, starting with a 5 molar stock solution? Now the term stock solution really means your more concentrated solution, the one that you would buy. So let's write out a list of things that we know. The solution we want to end up with has a concentration of 1 moles per liter, and it has a volume of 0.500 liters. This is 500 milliliters, and I have to convert that into liters, so I convert that over to 0.500 liters. So this is what I want to make. So what I'm starting with, the concentrated solution, is 5.0 moles per liter. And what I need to figure out is how much of this concentrated stuff do I require in order to dilute it down. So this is how much concentrated volume do I need. All right, so let's do this calculation. So we're just going to go C1V1 is equal to C2V2. I'm going to do my algebra before I substitute anything in here. So I want to isolate V2. So I'm going to divide C2 across to the other side, and that'll cancel that out. So now what I have is the volume required to make the solution is C1V1 all over C2. Let's substitute those values in. So I've got 1.0 moles per liter. I'm multiplying that by 0.500 liters. I'm going to double bracket that so it follows bed mass. And then the concentration of the more concentrated solution is 5.0 moles per liter. Now, if you look at the units, the moles per liter will cancel out with the moles per liter. And so the volume I'm going to be left with is in liters. So let's take a second to pause and do that calculation. Okay, so what I got was 0.100 liters, or 100 milliliters. So let's talk about how you go about actually doing this in the lab. Now, this is a fairly large volume, so I would probably use a graduated cylinder, 100 milliliter graduated cylinder, in order to get my concentrated solution and then transfer it into a volumetric flask. So what I would start with in this case, because I have 100 milliliters, I would have a 100 milliliter graduated cylinder. It would be nice to have something a little bit more accurate, but this is a large volume. And I would add in my 100 milliliters of 5.0 moles per liter H2SO4. Then, so that would be my first step. Then I would have my, I know it's a funny looking volumetric flask. Then I'd have my 500 milliliter volumetric flask. And what I would actually do is I would add a bit of water into here first. So I would add somewhere around probably 150 milliliters of water first. So I'd have a bit of water first. And then I would slowly add, in my third step, I would slowly add my H2SO4 to this water, and it would start to rise up. Okay, so I know 150 and my 100 milliliters of H2SO4 will combine for 250, and then I still have to add some more water after that. Now, this is a little bit different than our previous question. We never put water in the volumetric flask first, so why are we doing this now? And the answer is, when you dissolve an acid in water, it's extremely exothermic, which means it gives off a ton of heat. If you add water to acid first, it actually heats up the acid so hot it can cause an explosion inside of the vessel, and it could spray acid and glass all over you. So this step where we add water first, number 2, this is only something we do when we are making acids, or if we are doing anything that is extremely exothermic, because the water in here that I put in initially, it gradually distributes the heat around the solution, causing it to be a much safer process. So again, this would only be for acids. You would add water in first, and then you would slowly add, in step 3, you would slowly add the acid in gradually. This thing gets really, really hot, and then you allow it to cool down. You'd add some more. You'd allow it to cool down. You would add some more, etc. Okay. In my 4th step, I would top up the solution to the fill line. Okay, and then I would cap and invert 10 times. So that's how you would make a diluted acid from a more concentrated acid. You can also do this with other types of solutions that are not acids. You could take copper 2 sulfate pentahydrate, for instance, make a concentrated solution of that, and then add water to it to dilute it. And we would use what we call the dilution equation, which is C1V1 is equal to C2V2, in order to figure out the concentrated volume that we need to dissolve. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.